Okay, well, good. Well, thanks everyone for coming. It's another one of our weekly seminars in the bsac, sponsored by the bsac program. And we have a great crowd today, and we have a special guest who is a Berkeley alum. So I guess you said this is all new from where you were here, right?
I think the whole fourth floor has been remodeled.
Okay.
So
It's been a little while.
It's been a little while.
So she was here, but anyway, this is Debbie Senesky, Professor Senesky. She is an associate professor at some school across the bay in the aeronautics and astronautics department, but also has a courtesy appointment in the W department over there. She's the principal investigator at the Extreme Environment Microsystems Laboratory, or XLab, which is a pretty cool name. And she works on, or her lab works on the development of nanomaterials for extreme harsh environments, high temperature electronics, and robust instrumentation for things like Venus exploration. So I remember her talking about the electronics that were on the Venus Explorer. So it's definitely a harsh environment, probably one of the harshest, I guess. And she got her Ph.D. degree, as I say, from here at Berkeley. I won't mention the year, but it's
Okay.
a couple of years ago.
Yeah, we're doing it right.
And she's the co-editor of the IEEE Journal of Microelectromechanical Systems. So some of you may have submitted papers to that. So be nice to her. She's the co-editor if you want to get anything in the future. And also a Sensors Journal. So with that, I want to welcome Debbie.
Great. Thank you. Thanks so much, John. And yeah, thank you for having me and feeling lots of nostalgia because I was a PhD student here at Cal. Okay, I graduated in 2007. And I also was a postdoc here. So I joined Stanford in 2012. So lots of nostalgia. I remember the sandwiches and and coming to the bsac seminar for the sandwiches. And I think this room was the clean room. Is that right, Leeway? Was this this portion? Was this clean room facility when I was a student? So come up on the fourth floor and walk down and log into the micro lab back then. And then during my postdoc years, transitioned over to the Marvell clean room. So I was there during that journey and happy to share I haven't been actually here at bsac since 2012. So it's nice to share. This will be really the journey of what my group has been up to over the last 11 years. Wow. So I consider myself a child of the age of the small. So when I was entering Berkeley in 2001, I was really inspired by, all of the activity and leveraging IC fabrication to create micro electromechanical systems. So things that move, free suspended cantilever beams to make electrostatic drives, right? Comb fingers. Maybe you guys have manufactured things like that here. I don't know, maybe it's out of vogue, but the concept of making little moving machines at this scale. My advisor was Professor Pisano, who's now dean at UC San Diego. And we did we were based in Echeverry Hall and then would come over here for clean room to manufacture our MEMS. So this is, the technology. I think this is a gyroscope. And then after I graduated, had no interest in academia, although, Professor Pisano wanted me to stay on and continue the research. I ended up working at GE making pressure sensors for healthcare and automotive applications. So just a little bit about my history. I think this is your work here, Professor Nian. Is that right? No? Yeah, you suppose? Okay. So I'm referring to, the roots, the background. And then Professor Howe is now, we're hanging out at Stanford, but we used to hang out here back in the day. So these little machines are part of our everyday lives, right? So you guys are likely carrying your smartphone with you, where you have over, I think the last time I counted, it was 13 sensors that you're carrying around. And these sensors are collecting information about the environment around you. Also, information about how you're interacting with the phone. So accelerations and also angular accelerations through accelerometers and gyroscopes and magnetic fields, etc. Okay, so sensors are great. How do we use sensors, or how do we aim to use them? Where's the field going? So the idea of being able to collect information on our industrial system. So people say the industrial Internet of Things, but maybe now this is even outdated, and now we're calling it artificial intelligence and machine learning. This idea of collecting data, that's an important aspect of it, right? So being able to understand the instruments around us or the machines that are located around us. So these are some of the things that my group thinks about: the idea of deploying sensors on our industrial systems, collecting the data, analyzing the data, and the ability to react on demand with our human and physical networks. So the ability to prognose, diagnose, and also control the machines of the future. Oh, but unfortunately, a lot of our industrial systems have harsh environments within them. So this is a slide I made actually during my time at bsac, in the end days of my postdoc, thinking about where I can take my PhD work and postdoctoral work. What are the important applications? And I saw this opportunity in the extreme. And so, can we collect information that we cannot collect with our traditional silicon electronics? And so these special locations are subsurface, so oil and gas and geothermal wellbores, also in our power and propulsion system. So this would be aircraft engines, automotive engines, although these are moving now to more electrified systems. And so this is still relevant, although the temperature points wouldn't be as high. And then I also became very passionate about space exploration as well. So I'll touch on that throughout the talk. But these are a lot of the industrial and aerospace applications that drive my work. And again, the ability to collect data about combustion processes, subsurface properties, critical components, space environments. And then we would be really stressing our electronics, and the idea of being able to stress these electronics and still collect very, very important information. And again, our traditional silicon-based electronics cannot function above 200 degrees Celsius. You can push that up to slightly higher temperatures using a silicon on insulator process. But at these temperatures, you're going to start to generate thermal carriers that dominate the electrical properties. And so it's difficult to transduce within those kinds of temperatures. So when I joined Stanford in 2012, I came across this paper that showed gallium nitride operation at 1,000 degrees Celsius. So I thought, wow, this is really cool. Back then, I don't have time to talk about it, but during my time at Berkeley, I was working on using silicon carbide, which is another wide bandgap semiconductor material, to make extreme environment electronics. But I was starting my own lab, so I thought, okay, maybe I'll do something new and kind of jump on the gallium nitride bandwagon. So I'll talk you through what that journey has been. And I was really captivated by this work, right? The ability to transduce, create a transistor at 1,000 degrees Celsius. So these are the current voltage response. So the gate current up to 1,000 degrees Celsius. So the black curve is room temperature. all the way up to 1,000 degrees Celsius. And then if you hold that at 1,000 degrees Celsius, the evolution of the gate current. So this is, after various heating cycles. And so we're seeing that these curves overlap, which is nice. That's what we like. But unfortunately, this is in vacuum. And so a lot of the industrial applications that I showed you earlier, we can't leverage vacuum, right? We have hot oxidizing, very chemically corrosive environments. And so this is something that I really wanted to explore through my lab. How does gallium nitride measure up in terms of our modern day semiconductor materials? So this is our silicon here, our band gap of 1.12 eV. Again, that translates to around 200 degrees C thermal limit, whereas gallium nitride has a wider band gap of 3.4 eV. Also the very high melting point. It takes a lot of energy to break apart the gallium and nitrogen atoms. And also this also enables its radiation tolerance, which is nice. The 3.4 eV also translates to the ultraviolet spectrum. So the ability to make UV photodetectors that function at elevated temperatures. This was really attractive to me. And again, of course, silicon carbide, aluminum nitride, diamond, these are also wonderful wide band gap materials that I think are relevant and should be explored for extreme environments as well. And there are other groups, including my own, that are looking at these other platforms. But today's talk is really focused on gallium nitride. And so gallium nitride is a semiconductor platform that has been developed primarily for the power and RF communication sectors, and also the blue LED. So Nobel Prize winning work for gallium nitride and the discovery of its optoelectronic properties. And so my group is really looking at it for different types of applications, sensor technology. The highest efficiency solar cells actually have a layer of gallium nitride in it because, as I mentioned, it's sensitive to the ultraviolet band. So you're capturing not only IR, but the ultraviolet spectrum. Micromechanical resonators, so leveraging the piezoelectric properties to make vibrating machines, and also nanostructures. Other groups are looking at using gallium nitride for nanostructures. So I also want to tell you a little bit about why gallium nitride is different in comparison to your traditional silicon CMOS technology. So in silicon CMOS, you're usually relying on doped junctions to create your transistor or your transducer. Whereas gallium nitride, the transduction is a little bit different for the heterostructured class of gallium nitride-based electronics. So something we leverage here for transduction is the two-dimensional electron gas. So this is, again, different from a doped junction. And this two-dimensional electron gas, which is a highly conductive sheet of electrons at the interface of a heterostructure. So let me go back. So we have our heterostructure here, aluminum, gallium nitride, and at the interface, this two-dimensional electron gas. And this is formed due to two phenomenon: spontaneous polarization. So if I look at a gallium nitride unit cell, we have elongation and there's a dipole that's generated. And also we have piezoelectric polarization as well. So if I grow that slightly doped variant algan on top of gallium nitride, due to the lattice mismatch, we have tension in the film. And due to the piezoelectric nature, we're generating a voltage. And the combination of these two effects form this quantum well at the interface. And this is how, again, we have our conductive two-dimensional electron gas, or our 2-dig. And so we're often wondering, is the nature of this 2-dig, especially at high temperature, high temperatures. And so this is some work of our sheet density. So N sub S, a sheet density. So the blue dots are for algan GaN, stable room temperature up to 600 C, and this is collected in air. And then a slightly doped variant, different dope variant, indium aluminum nitride, gallium nitride. So we can, again, change that top layer in the heterostructure, has a slightly higher, but also a constant sheet density as we move from room temperature up to 600 C. And this data in particular is collected in air. And then, of course, our mobility does degrade, as with any semiconductor material or transport of electrons due to scattering effects. That's just the nature. We can't really get around that. So we do have mobility degradation, and depending on the type of device, that might be important. But nonetheless, we do have carriers, room temperature up to 600 degrees Celsius. So these are the two, kind of knobs that we look at and try to understand when we start to stimulate these types of devices with the external environment. I'll show you. Yeah, that's an ongoing question. I'll talk about the failure modes, but our longest test has been around 10 days or so. So that's pretty good, but still lots to do. And I'll touch on that throughout the talk. So this is a cross section of a high electron mobility transistor, so HEMT. So I'll start to use that terminology now. So our GaN HEMT, high electron mobility transistor. We do a lot of work to be able to grow it on silicon. So we use a silicon 111 substrate to lattice match as much as we can. And then we grow a series of interfacial or buffer layers to enable integrity of the algan GaN layer. This would be our device layer up here, right? So we have our algan GaN, and then our two-dimensional electron gas, and then these are called strain relaxation layers. So strain engineering, preventing strain relaxation. So our strain engineering layers, we're slightly grading the dopants in order to transition so we don't get cracking or strain relaxation in our two-dimensional electron gas, because strain is important. As I told you before, it's piezoelectric. So we need strain for the 2-deg. But if strain changes, that changes the properties. So that's something we are very careful about. So the transistor now looks like source, gate, drain, passivation, algan GaN, and then our two-dimensional electron gas. And we can modulate the sheet density through activation of our gate. Okay, so now you guys have the GaN transistor under your belt. My background is in MEMS. As I told you before, I like releasing the substrate. So again, when I joined Stanford in 2012, I thought, wow, can I use this high electron mobility transistor to transduce, to make sensors that can collect data within harsh environments? So we embarked on this journey of integrating MEMS fabrication techniques and also high temperature metallization and passivation to the high electron mobility transistor. And so you monolithically integrate pressure sensors, transistors, surface acoustic wave resonators, photodetectors, heat flux sensors, accelerometers, chemical sensors, all on the same chip in one fabrication process flow. And so we've accomplished a lot of demonstrations in this work. So pressure sensors, UV photodetectors, Hall effect sensors, thermoelectrics. These represent a PhD in my group, roughly. And so I'll walk you through some of these examples. There are more. I won't have time to go through everything. But again, we are leveraging MEMS fabrication techniques. So leveraging the ability to etch out this silicon substrate. And so this is a cross-section of our fabrication flow. We do this in the Stanford nanofabrication facility. We can grow our algae GaN in-house, but oftentimes we just buy the substrate. You can buy these commercially. So if anyone's interested, you can have an algae GaN starting substrate. You can, etch the mesostructure, put down high temperature ohmic contacts. There's a lot that goes into that. Gate contacts, we've explored a variety of high temperature gate contacts, and then a passivation layer, we're using aluminum oxide. And, when you start to stack up these materials and operate at high temperature, you start to think about how all of these materials work together. Interconnect material, masking for the backside, release of the backside, and then you have your nice device. And so all of my students can piggyback and yes, go ahead. Question. The buffer layer, which buffer layer are you referring to? Yeah, so the buffer layer would be like this aluminum nitride here, but it's not like, sure, that's a nucleation layer. Then yes, you need those, absolutely. Otherwise they'll crack. Yeah, I'm not showing all the 50 steps, right? It's right here. It's like right in between. Yeah. So you do need the buffer layers, absolutely. Otherwise they'll crack. So using this fabrication process, you can start to make different types of transducers. This is one that we've matured over the years. So using the algae GaN heterostructure to create magnetic field sensors through the Hall effect. So instead of a silicon doped junction, you have now your two-dimensional electron gas as your conductive layer, ohmic contacts here, and this is your Hall plate. So if you expose this to a magnetic field and you induce a current across two sets of electrodes, the magnetic field will bend the trajectory of the electrons, and you can measure that off with a secondary set of electrodes. Unfortunately, when you operate this in a zero magnetic field, you experience or observe something called offset. And this is something that occurs with a lot of sensors, meaning that in a zero magnetic field, you have a voltage that's present. And that's something you want to mitigate. And so we use something called current spinning, where we're averaging out the response as we apply current around these electrodes. And then using this equation here, we can create a zero crossing. So it's basically an averaging technique. So where at a zero B field, we now have a zero voltage. And so this offset is something that my former student, now Professor Karen Dowling, she studied was, wow, how do we mitigate this offset? So what's causing the offset is the thermal gradient across the device. And so that thermal gradient induces the Seebeck effect, and that's how you have the voltage. So just by powering up the device, you get a voltage offset. So that's through the Seebeck effect. Silicon has it as well. It's something you just can't really get rid of. And then any resistance asymmetry in your device through fabrication. So this is the offset for silicon reference. And then you can see for our two gallium nitride heterostructures, really suppression in the offset. And then we did validation studies looking at thermal profiles across the device and translating to, this delta T across the device during activation and how that influences the offset. So aging, so Clark's Professor Nguyen's question, how long do these things work? So this is something we've carried on in collaboration with our collaborators at University of Arkansas. So we did a variety of tests. We had a bunch of our algae GaN Hall effect plates. We measured them at 600 degrees Celsius in air for various times. So this is what you see here. This is temperature. Sorry, this is actually time. Sorry. So holding at 450 degrees Celsius, we see this burn-in period and then stabilization of the resistance. So this is telling us that our ohmic contacts are remaining stable over a period of time. And this is for a variety of our Hall effect mobility family devices. So these represent different shapes of our Hall effect. And then we've also done short duration tests. So this is up to 368 hours. And then this is short duration tests where we cycle room temperature up to 600 degrees C in air. And we can see the voltage scale sensitivity is overlapping, but these are minutes of tests, right? This is on a probe station and we're able to ramp up and down, but we want to do much longer aging studies. And this degradation here with temperature is due to the decrease in mobility as we expect. We also studied the thermoelectric behavior. So another type of transduction. If we have heat gradients across the 2-deg, what happens? Can we use this as an energy harvester? And so one challenge with thermoelectric devices is the trade-off between resistivity and electrical resistivity and thermal conductivity. So what my former student Anand Yalamarthy conducted was, can we change the thermal conductivity of our gallium nitride by changing the thickness of our gallium nitride layer? So if we have a thick gallium nitride or a thin gallium nitride, that will change the temperature gradient or the thermal properties across this film here. So we have our thicker GaN, we're calling it our bulk GaN. We have a high thermal conductivity. And as we move to a thinner layer, we have a lower thermal conductivity, and that's due to thermal scattering between these interfaces. However, we're able to maintain electrical conductivity. And that's the beauty of the 2-deg, the two-dimensional electron gas. We still can maintain our sheet density, even if we change the thicknesses of those films slightly. So this idea of being able to tune the thermal transport and maintain the electrical transport. And so the figure of merit of thermoelectric devices is one figure of merit is the ZT coefficient, where again, we have a trade-off typically between resistivity, electrical resistivity, and thermal conductivity. And then again, we show that for a thin gallium nitride, we get a boost in our ZT coefficient. And we tested this out using MEMS fabrication techniques where we created this suspended AlGaN-GaN membrane here. We machined these platinum heaters. So we created a hotspot across these purple two-dimensional electron gas thermoelectric structures. So this is the hot side, and then the substrate, the unreleased portion, is the cold side. And then we can model it, see what the delta T is, and oh no, battery's running low. Maybe we can plug in there, hopefully. So we can measure the temperature gradient and also validate it with our finite element modeling as well. And this translated to power factors between 4 and 7 milliwatts per meter Kelvin squared. So this is, we're happy with this number. So the idea is, could we scale these thermoelectric devices up, stack them up and actually harvest heat gradients? Thank you so much. Hopefully that, great. Okay, we have our charge here. So hopefully I showed you a couple of examples of using the AlGaN-GaN two-dimensional electron gas to make magnetic field sensors, heat flux sensors. We've also made a variety of other sensors. But I'm going to shift gears and talk about another application. So Venus exploration, as I mentioned before. So we've been actively involved in the NASA Hot Tech program, Hot Operating Temperature Technology program, with a variety of collaborators that are also in the MEMS and microelectronics community. This is an image of the surface of Venus. This was taken in 1982 by a Soviet lander, so via the Venera 13 mission. It might be the 14 mission. I need to verify, if someone corrected me about that these images were from the 14 mission. But nonetheless, so this is the surface of Venus. Venus is our neighboring planet, but it has an atmosphere that is very different in comparison. It's okay. We're getting our power here. Darlene's hooking it up. We're there. We're good. Thank you so much. So Venus, okay, Venus is our neighboring planet. You can see here the image of it. It looks very different from Earth, right? You can think of it as a very hot volcanic type environment. The surface temperatures are around 480 degrees Celsius. The climate is filled with supercritical CO2 and sulfuric acid. So this yellow haze here is kind of like I imagine it would smell like rotting eggs on the surface there. And this was a color image that was, again, taken from this mission that only lasted 2 hours. And this was because of the degradation of the electronics. So again, with our 10-day test, we're super happy with that because that's way more than this 2-hour mission. NASA is interested in a 2-month lander mission to create a video that would give scientific information about the weather patterns, temperature gradients, and they chose 2 months because it's roughly a quarter of a Venus year, so get 1/4 of a year. And so you could see the time constraints, right? We can't land something there for 1 year because of the constraints that we have with our modern day sensors and microelectronics. So there's a community of researchers that are interested in understanding what are the right microelectronics platforms that would enable this kind of lander style mission. This is a Venus simulation chamber that's located in NASA Glenn in Cleveland, Ohio. It has all of the chemical constituents, the pressure and temperature of Venus. So the pressure is 90 bar. I don't know if I mentioned that. So high pressure environment, high temperature. This is really challenging for our modern day electronics. And so to study this, we recently just wrapped up an 11-day test in a Venus ambient. It has the CO2, it has the sulfuric acid. So this is the pressure ramp and the temperature ramp. And so 11 days that is actually representing the Venusian ambient. We placed our gallium nitride high electron mobility transistor alongside an MIT device as well and an ASU device. So these are all wide bandgap materials. And yeah, we need a Berkeley representation here, right? Sorry, we have all the schools here. In spirit, I'm carrying on the Berkeley flag. But yeah, so we have mounted our gallium nitride chip here, a lot of work in wire bonding, selecting wire bonding materials, ohmic contact materials, gate contacts, one device, we're doing this test, lots of teamwork here. And then we insert it in the chamber and I can't show you the data today, but we're in the process of analyzing that data. But that data, all 3 devices ended up working. So we're really excited about that. And we're studying, shifts in threshold voltage and things like that over the duration. And this would, again, potentially lead up to answering questions like, would gallium nitride work for a lander mission? Would diamond, would silicon carbide? So it's been fun to be a part of this community, understanding the science goals and, that NASA imparts on the community and then building the technology to do that. So one vision is, what if we had this sensor node that had seismometers or vibration sensors, pressure sensors, temperature sensors. They already have a lot of that covered through NASA. And so, looking at other important aspects as well. So Dr. Mina Razadeh from JPL and I we combined forces and we wanted to look at a transmitter component. And so in particular, clock technology or resonator technology that would be viable for this type of environment. And so we have a variety of devices that we've built over the years. But one device that we've tested was a surface acoustic wave resonator. So you have your interdigitated transducers and your reflectors, and again, leveraging the piezoelectric properties of gallium nitride in order to create this surface acoustic wave on the surface. You can use topside metallization, or now you can also think of using the 2-deg as the metallization or the conductive layer as well. We bring these over to my lab for testing. This is a high temperature probe station that we have in my lab with RF probes. They're tungsten. There's a lot of work, they're actively cooled. A lot of work just in the testing, right, and getting this right. And this is in air exposed. And so this is the frequency response, room temperature up to 500 degrees Celsius. You can see we're able to have this device resonating and demonstrating and measuring the fundamental frequency, but we do see a degradation in Q factor over time, and also a shift in the frequency as well as we're heating up the device. So these are the things we want to study and compensate for. But nonetheless, again, yes, question. Say it one more time. Why is it at negative 50 dB level in terms of this axis here? This is the S21 parameter. And so I guess the question, why is it negative as opposed to positive? Or why is it so negative? Probably because this is like not a great device, right? It's not, it's not one that is, Mina's looked at a lot of like different types of releasing the substrate, and those are going to have like really higher performing dB levels. So I hope that answers. Yes. Yeah, a variety of things. So damping, as you heat up the material, it's softening. And so there's going to be, just dampening effects inherently around the material. We've not done anything in terms of like, a lot of engineering the wave into the material. There's probably leakage in the substrate and things like that. So these are things that we're ongoing, translating a lot of work that has been done at lower temperature, at room temperature, and translating it to high temperature. But this is, very lossy system here. Yeah. And then just looking at temperature, coefficient of frequency, as you expect due to softening, it does shift. And then also our nickel contacts, we observed degradation. These were not highly optimized contacts at the time. We did some, how am I on time? Just want to make sure we have 10 minutes. Okay, I might flash forward because you guys have seen some of the Venus stuff, but we've done other tests. This is a transistor that we tested in another Venus chamber, pre and post exposure. These are our ohmic contacts, a aluminum, molybdenum, gold, iridium oxide gate. So looking at really complex gate materials. This is Savannah's work, recent thesis out of the group. Yep. Well, the gate material matters because a lot of gate materials will either sink into the, so you want a Schottky contact, right? But unfortunately, so you can create a metal insulator structure. We've done that. A lot of the metallizations just sink into this, top layer, which can degrade. And so we want a high temperature version of a Schottky contact. So we've probably studied most of them in the group. Some of them just flat out evaporate, like molybdenum, for example, they just disappear after time. So a lot of tricks in, like, do we passivate it? Do we need an MIS structure? Things like that. And then the ohmic contacts as well, a lot of art that goes into this. And so still lots of work to be done here. What we're seeing in the IV response is actually an increase in the drain current. And so we're trying to understand what are the carriers in the iridium oxide after exposure to supercritical CO2. So this is ongoing work, but nonetheless, these transistors actually work better after 10 days in supercritical CO2, and a lot of studying threshold voltage, pre and post. And then, as I mentioned, we just did our in situ test as well.
Like stage into the layers that actually have the action.
Diffusion, right? So creating a eutectic, depending on the metal, sometimes this evaporates. Iridium oxide doesn't sink. We're showing it's actually staying on top based on our Auger electron spectroscopy. So you do want to, create a eutectic, but you want it to be Schottky in nature and also stable as well. So more data. I'm going to flash forward. I'm going to skip to something I'm excited about in the last 5 minutes. So we're shifting gears. So we're leaving Venus and we're going to go to low Earth orbit in the last few minutes of this talk. So a new area in my group is looking at manufacturing in low Earth orbit. The idea of, can you make it in space and don't take it to space? Or can you actually, I'll flash forward. Can you actually make products for Earth as well? These slides are a little rough because this is all new. So make it, don't take it. If you're conducting a mission to Venus, can you make your electronics, your rover, your lander, all of your assemblies in space, and then conduct your mission? Can you use the resources you have around you to make buildings? And then another aspect is, can we leverage the low Earth orbit environment for products here on Earth? So just wanted to share this with you guys. This is a really new community that's forming. Microgravity is different. And so those of you who are using the clean room facilities, growing films, etching films, gravity is a part of your process. If you go to microgravity, gravity is reduced significantly. And so you suppress thermal convection, container interactions, hydrostatic pressure, buoyancy, and you also have access to vacuum. So what does this mean for synthesis of nanomaterials and semiconductor materials? This is one example. Actually, Dr. Carlo Carrera and Professor Roya Maboudian have shared, we're collaborators on this type of work. We found this paper showing a metal organic framework crystal, a MOF crystal, and this past work, expose it to different levels of gravity during the growth process, and they're seeing larger crystals under reduced gravity. And so that triggered us to really go back into the history of semiconductor growth and crystal growth. And if you go back 50 years, they were growing gallium antimonide crystals, large format, on the space shuttle with higher growth rates and also reduced defect density. So what does that mean for semiconductors? This is one case study. If you grow a cadmium telluride crystal using solar cell applications on Earth versus microgravity, in microgravity, you can get a larger area. Also, that translates to more usable volume of material if you're able to suppress the defects in the material as well. So again, the absence of thermal convection, your fluid as you're growing this crystal, creating a more diffusion-based growth as opposed to having defect sites during growth. And this would translate to more product, right, that we want to use here on Earth. We just wrapped a semiconductor manufacturing in the space domain workshop last week. So I just want to share this work, and also The White House, is just offered an announcement or made an announcement of low Earth orbit, supporting low Earth orbit commerce. And so I believe semiconductors will have a role in that. Professor Mabudian's here, Carla Carrera, also Professor Al-Balushi from MatSci. I don't know if he's in the photo. He may have left. And then we didn't quite get Roger Howe in here either. I think he stepped out during the photo. But just want to share this with the community that these activities are ongoing, and there's a community that's looking at the intersection of semiconductors and harnessing microgravity to create products for Earth. And we have, I'll wrap here, we have an ongoing experiment that'll be launching on SpaceX 28 in June to create graphene aerogels in low Earth orbit. And again, we want to overcome the gravitational effects during synthesis and compare Earth and space-grown samples. So I'll wrap, and hopefully I've exposed you to a field that is looking at extreme environments, not only to enable missions, but also, through high temperature radiation tolerance, can we enable the collection of new types of scientific data outside of Earth and also on Earth, right? Subsurface, combustion environments. And then can we also use extreme environments and leverage extreme environments such as microgravity to create important products for Earth as well. So that's it. And I want to acknowledge my group and the various funding sources as well. So I'm happy to take any questions. Yes. Yeah, we'll see. We're working on it. So, if there's interest, it's important to, right now we're knocking on doors in DC to bring awareness. We have the CHIPS Act, and, a portion of that should go to this activity. Right now, there is an opportunity to use the International Space Station for small scale demonstrations. Unfortunately, they're limited to lower temperatures, and with the astronauts there, it's very difficult. But there are 4 commercial low Earth orbit destinations coming online. So Blue Origin Orbital Reef, Northrop Grumman, Axiom Space, and then I think Starlab as well. So those are going to eventually replace the International Space Station, and so there's opportunities to design, hardware that would enable semiconductor fab there. So within the next 10 years, hopefully, or not sooner. Mm-hmm. Yeah.
Right. What are the theoretical limits do you think your temperature semiconductors at materials? Can you get them up to 1,000 C and get around to 4 or 2,000 or even at like 5,000?
Yeah, I think melting point, probably not, but let's talk about 1,000 C when really it's the carriers, the band gap, right? Having controllable carriers. And that's really, it's all about the metal contacts and the interaction between the semiconductor and the metals. And ohmic contacts, we're really happy about. We think we have that down. Again, we need to do longer duration studies, but those seem to be holding up very well. Ohmic contact, still a lot. Gate contact, still a lot to do, but I don't see it as impossible. And then understanding how all of these materials work in concert together. So there's a lot of reliability aspects that are very, very important. So I think that it's going to be more the 1,000 degrees C limit as opposed to, the melting. I think that's a whole other realm that I think would be tough to overcome. Yeah.
And apart from battery use and better quality itself, is there any particular or unique characters for materials or crystal grows in microgravity environments.
So what were the two, in addition to what?
Battery use, battery quality, yeah, but I'm curious about, is there any unique part or unique?
Yeah, I mean, there could be, right? So as I mentioned, what we've seen, because there was a study, they categorized all of the crystals and materials that have ever been grown. And, you know, the main, because everyone asks about costs. And so the main drivers are, you know, size, defect density, but you have all of this. So container interactions, we were actually talking with a silicon manufacturer. So silicon suffers from interaction with the quartz receptor. Even today, that causes us to throw away a lot of the material. Also immiscibility when you're creating alloys. I think that's another aspect. We're not in particularly looking at it, but as you have create alloys, right? You here on Earth, you have set of, you can't like, you know, the material just can't absorb or you know, you have buoyancy issues on Earth. And so can you now create that alloy that you couldn't create? So I think creating new types of materials will be interesting. You know, how we create them, will we leverage the vacuum of space? How do we power? Again, yeah, so all of these, I think there's open territory here. Yeah. Yeah, so how do we maintain the temperatures during our measurement? So we use very special equipment. Our probe station is a high temperature probe station that's rated to 600 C. So the chuck itself has a power supply that enables it to work at 600 C. And we use very special tungsten probes. For the Venus chamber, we rely on NASA. They have a whole interconnect technology. So we go from a wire bond to a board, and then they connect to our board. And there's like a lot of engineering that goes into that to have in situ. It's actually really hard. Yeah. Mhm.
Over what time scale?
Yeah, I didn't get a chance to cover that. We focus a lot on temperature in my lab, and it depends on the environment that you're looking at. So for things like Europa, which is the icy moon of Jupiter, it has a high radiation field. So those are going to be mega AV particles, high fluence, whereas in low Earth orbit, you know, it's actually, you know, in terms of the particulates, there it's actually not that bad. There's a certain total ionizing dose number, I don't know it out of the top of my head, that you would have to design for 1 year of life, so understanding what that is. But you might have anomalous high energy particles that might hit your electronics, and just there's nothing you can do about it. It's going to just blast through your entire electronics. So understanding that there's a cocktail of radiation out there and gearing it towards your application. You may have redundancy. You may still have some level of packaging to account for any anomalous effects that might happen. You can also do fun things at the circuit level as well. So that's how we tackle radiation, but it is also really hard to do and not like a clear solution. Yeah.
Earlier slide. Soon to be pretty hard. Yes.
Yeah. Yeah, you know, I agree. That's a really good point, right? We just kind of throw it out there, but I think for some of these materials, it's still yet to be seen. We still package them. Also, the defects in the material, because a lot of these materials, we're still learning how to grow them without defects. So silicon carbide, for example, has micropipes, and that actually can be risky in a radiation aspect, and also gallium nitride. There are deep level traps within the material that can be excited with either temperature or radiation. So yeah, we kind of just throw that around because it has a high atomic binding energy, but it's the nature of the film, the nature of the environment, and how the carriers react to radiation. So those are opportunities for studies as well. Yeah. Okay. Other questions? All right,
Well, thank our speaker again.
thank you.